cool. So the other bit, and this is one of my ex-students, Gotham Vassar, who's now at Kindred, who's trying to shake hands with the robot, and what you'll notice is that that robot handshake is just abysmal. That's a really bad handshake. I would think that was a good handshake. And so another piece that we often talk about, we talked about learning, we talked about intelligence, and we didn't talk about why learning is actually a good thing. We had a few comments at the beginning and a few comments during our like what is intelligence part about why learning might be good. But I'll try to break this down as well into 3 things. You can tell like 3 is a number I can hold in my head. Any more than that, it gets all wonky. But one reason why people might appeal to machine learning and not just a general form of machine intelligence, and one of them is that we might in fact have to answer phone calls in the middle of a, no, kidding. Is that one thing is that we might know what we want as designers, as developers, as people implementing a system, but we might have no idea how to get it. Like imagine that I'm here and I need a robot arm to pick that up, and like, I don't know, maybe the robot arm is a really complex robot arm, maybe I'm a really bad programmer, which is true. Maybe the robot arm is like a giant tentacle thing that I can't even figure out how to control. I know when the tea is in my mouth, but I may not know how to get the tea in my mouth. So machine learning is one way that we can begin to find ways to solve problems where we know the thing we hope to achieve, but we don't actually know how we wanted to get there. Okay? Another piece is that maybe we actually do know how to solve the problem, but scaling up is really, really hard. Like it's something that we know a team of really good developers could actually do, but it might take that team of developers 6 years to make it happen. And then as soon as they did, maybe the system changes, the world changes, the design requirements change, and they have to spend another 6 years changing the system. Maybe even 2 years changing the system. Either way, we may know how to solve the problem, but doing so is beyond our scale of resources. And the last bit is the bit that I think is really important, is that things change all the time. The world changes, we change, our needs change. Devices that are deployed within the real world, technologies that are deployed within the real world, need to adapt to the real world. And that's something that in many cases just can't happen no matter how good you are at building in constraints in the factory or before a product is launched. So systems actually do need to change. And learning is a great way for systems to change. And this came up during our comments earlier, our discussions earlier. Okay, cool. Is that any questions on that? Sorry, has anyone actually worked with machine learning? I should have asked this before. I could ask you to come give the lecture. No one's played around? Why? Okay, so sidebar before we go into the next piece. Why has no one played around with machine learning?
Because we're not in computer science.
Oh, I thought that was going to be the answer, and that makes me super sad. So was it tricky? Was it too hard? Like, is there a perception that's really like hard to get started, or?
Wasn't able to get consent from my computer.
Oh yeah, that's really hard. They had to sign those forms, aren't they? So everyone like, no? So let me pitch some other things. Like, do you feel that there's very poor resources for getting started? Like, who would actually want to play around with machine learning and machine intelligence? Show of hands, maybe. You could say no. You'd be like, no, I don't really care at all, actually. I'm going to be doing that like nanotech stuff we talked about earlier in the course.
It seems very, like, don't you have to take steps to get there, like all the comp sci courses before, and then machine learning is kind of like the end goal? Like, it seems like something for a comp sci student, and at the end, you're like, okay, now I have the skills to do machine learning.
I think that you're absolutely right, that's how it's viewed. And I think that means that we as a community have completely failed everyone, including you. Because I don't think that actually, like, we're getting to the point where I don't think that's the case. So that's really cool. I mean, people can also, who's programmed? Maybe this is a good analogy. Okay, you programmed, written code. What kind of code did you write?
Well, I'm in comp sci like 174 right now, just like very basic. Like, I literally learned like if else and like while loops and for loops, like just really, really basic.
Cool, and that's like, is it Python?
Yeah.
Oh, awesome, I like Python. I actually almost rock Python. I'm pretty bad at the rest. So I'll use an analogy. This is again sidebar time. It's like mid-lecture chat time. So the other day I came home from work and my wife, who's a communications professional, was sitting on the couch with her iPad. I'm like, oh, cool. Hey, sweetie, what you doing? She's like, oh, I'm programming apps. She's like, I'm going to be an app designer. I'm learning Swift right now. I was like, sorry? She's like, yeah, I'm learning Swift. It's really easy. And I looked at it, like, it's arguably hard to learn to program, but she was already halfway through the entire first module and had like all these different like loops set up. She was even using data structures and had like objects hopping around in a little app window. Because Apple had done a great job in this case of building an app that taught how to use Swift. And so this is one example, like, hey, like programming, actually the barrier to entry to programming is becoming lower and lower, and people are doing a good job trying to make it accessible. You can think that machine learning maybe isn't actually anything more than just programming with a few extra routines or modules put in if you really want to get started. And so it's interesting to, like, this is exactly what I expected. People are like, oh, it'll be really hard, I have to take a comp sci degree, right? And interestingly, if you even have a even rough handle on Python, you could just go online, get OpenAI's gym or something, and you could probably be up and running with a learning machine in under an hour or two. But nobody, like, that seems to be not a common perception, and so I think we're only going to see more people who need to know how to begin to access technologies that can adapt, can scale up, can solve problems. I've used it before everything, like when my wife and I were getting married, I wrote a quick Python script with some adaptive learning, like to learn to balance the different wedding planning options to find like cost maximum for different guest levels. And like there's all these little tiny like life hacks that we can do when we start to use the technologies, but my sort of poll of the room, this sounds to me like that still doesn't feel accessible to everyone, and we as a machine learning community need to up our game. Is that a fair statement? Yeah?
Just like a side note, my friend's in education, and as part of the education program now, they actually have to learn how to code, and they're going to start implementing that in like elementary and junior high education. So yeah, the problem will be solved soon.
Cool. I also, there's hope as well. I was doing some outreach at a high school, and one student had a project which was he was building it was essentially a mirror that also had a TV screen projection through it, so trying to build like essentially a smart mirror, and was going to build a Face ID system, much like Apple's Face ID, to sort of take a camera images of the face of the person using it, map it to some feature space, and then try to figure out if it was the person who's supposed to be accessing the smart mirror or not. This is at high school and actually managed to nail the project, and it was really cool. So I'm optimistic that people are going to find more and more accessible ways to do this. But okay, cool. Thanks for the sidebar. This again, part of the role of Amy, and I'm sort of wearing my Amy hat right now as well, is that the Machine Intelligence Institute is trying to build better outreach and upskilling programs so that everybody can start to figure out how to access machine learning technologies and deploy it for the problems they care about. So this is a good little data point. I'm going to file this in the back of my mind. So I appreciate that. Cool. All right, let's get back on track then. And we'll talk about maybe the last piece of this, and then we can have question and answer time and wrap up with some time to spare. So I've thought a lot about this, and I tried to decide really what my job is at the university. And I think one of my jobs at the university is just to talk about this. Maybe not even be right about this topic, but to just talk about and continue to talk about the topic of how AI and machine learning are and can be used in medicine. So I'll do the last, say, third of my talk now on that particular topic. And one of the first ways that I've started to break down the utility of these technologies in the entire medical arena, and especially in the realm of physiatry, is generalization, personalization, and optimization. Now, I'll sort of unpack each of those in turn, and we can talk about them. But the first really, and I'm calling this generalization, whether or not it's the right term is up for grabs, I guess. But one thing that advanced intelligent technologies like machine intelligence can do, it can help us understand whole populations of patients. Maybe I give you all of the health data from a bazillion people and say, extract out the core lessons from those populations. How do at the population level, how do different ailments or complications, how do they vary with different patient demographics? Looking at population level generalization of data to bigger or more abstract trends. This is one way that we can imagine, especially you can imagine healthcare professionals and health governance being able to understand patients at the population level. Okay, this should be a very common, like a lot of things we probably hear with respect to AI medicine may start to operate on this level. This is maybe the things that you've already heard about. And also understanding individual patients. I've spent a lot of my research career working on various technologies. We did like tricorders, lab-on-a-chip technologies to diagnose cancer based on individuals and like try to structure the dosing for those individuals based on their actual genetic structure or the layout of their cells. So like those kinds of endeavors can be thought of maybe more as personalization, which is truly understanding individuals. And once you can understand individuals, you can begin to relate that to the general trends that you found in populations of individuals, populations of patients. So I think really generalization and personalization are two very important parts of this. The third is more or less what I work on now, which is optimization. Finding ways that you can optimize, say, the connection between a person and their assistive device as they go on living their life, or in optimizing treatment strategies or measurement strategies to individuals. So this sort of links between the generalization, personalization, and then optimization to those individuals, given that knowledge of them and how they relate to the other individuals in a patient population. So I think these are three big areas. Again, I encourage you to disagree with me on whether or not that's the right way to break it down, but as one particular slicing pattern through the utility of these technologies in medicine, I do think we can understand groups of individuals, and then how to modulate our treatment patterns to those individuals. Who's familiar with the Human Connectome project? Neuroscience? No? Okay. Yes? Okay. One. Do you want to say anything cool about it? No? Okay. I think it's really cool. Mainly look at these awesome pictures. Like, it has to be cool if they make these really pretty pictures. But the Human Connectome project is really looking at the brain. So I'm going to use this as an example, maybe a poor example of generalization, but by looking at various different measurement technologies to try and understand how the human brain connects, how all the wiring in the brain happens, how one part of the brain connects to the other part of the brain, like the cerebellum is connected to the other thing. Anyway, how the different parts of our nervous structure, actually the neural tissue, connect to other parts of our neural tissue. You could view this as an act of generalization, trying to get general lessons about how humans writ large are structured in terms of their central nervous system. You could also imagine scanning any individual and then using advanced computing technologies like machine learning, machine intelligence, to start to see how their individual brain structure maps to our common general understanding of how brains wire, or how different groups of brains wire together. So that's one example I like to use of the relationship between personalization and generalization. You might imagine someone comes in with a traumatic brain injury, or someone was born without part of their brain tissue, or someone who had their corpus callosum cut and now has two parts of their brain that operate independently. You might imagine that you could then compare their connectome to the general connectomes that we have measured. And that would be really hard to do. Like if I was going and be like, oh cool, look at all these little wires. Okay, where's that blue one go? Does that blue one go over here? To do this manually would be really, really hard. But our intelligent systems technology can begin to understand the complexity of those patterns and begin to find ways to register, to compare, to understand the wealth of data in something like the Human Connectome project. That cool? That's just one example. Another one, this is actually, again, I'm not wearing my DeepMind hat right now, but one thing that we recently saw out in the literature was very accurate, rapid diagnoses of eye disorders. So being able to have intelligent systems technology that could begin to look at individuals and begin to diagnose, in this case, trouble with their eyes to the same level as clinicians who had been 20 years of experience in the field. So 20 years of experience and have systems that can begin to do that with less errors. So this was an example again of taking in large amounts of health information, being able to assess the key patterns and then fit that to individual patients. Recent work as well on detecting kidney failures like 48 hours before the kidney is actually failure. So you can start to actually provide treatment before it becomes critical. And the examples, this is some of the work we do in the lab over in the Cates Group Center, which is looking at how we fit prostheses to individuals and make situations like this. Is one of our participants coming in who's using a standard or a very conventional control method to try to put all the little ball in the cups. And as you can see, it's really slow and painstaking. So as an example of optimization, one thing that we've been trying to do is to take individuals who are using conventional or standard prosthetic control methods and allow the system itself to start to get better with time. As a person uses it, allow it to start to streamline or structure the way the person interacts with the device so that it takes less time, less effort, less cognitive burden, or less frustration for someone to say complete a task like this one where they may just be putting balls in cups. Because I mean, I showed you some robots earlier. This is one of the robots we have in the lab as well. And it's not, again, I'm going to argue, it's not that we don't have awesome robots. Like a robot like this can make, arguably to a first approximation, many of the movements that we'd expect from a biological limb. So it makes a lot of like clanking noises. Yeah, please. Sorry, I'll turn this off so it doesn't make that clanking noise.
It's okay. Is it just practice makes perfect? So as the person who uses it, their brain understands how to make it work the way they want it to?
Traditionally, yeah. I mean, and maybe this is what I'm saying that we can now do better. Is that, in fact, most of the time it is like if I have a new tennis racket or I have a new car, I have to figure out how to use my new tool. I'm adapting to the tool. For the history of our species, we've pretty well adapted to tools. Some tools, you could call them tools, I'm not sure, but like agriculture, we have livestock and things, maybe they adapt to us too. But we're now in a position where not only can we adapt to our tools, but we can start to study how our tools can adapt to us. And through that co-adaptation process, maybe we can do better. And so that's really what we're looking at, is finding ways to both design and measure interventions that allow the tools to begin to also adapt to the person. So that's the learning aspect of things. I mean, you could deploy a prosthetic limb that does watch how someone uses it and then start to give them what they want when they want it, to reduce their efforts. So yeah, it's a co-learning process. But you're right, you can't decouple the human learning, because that is a huge part of it. And we see people that don't have adaptive tools that still can over a lifetime become a level of finesse with their use of their tools that will still surpass any of our co-adaptive systems. But we should expect good things from co-adaptive systems, I guess, is the hypothesis. Maybe you don't buy it. But.
No, it's just because you see one hand is moving so smoothly, and then the other one's kind of glitchy.
Yeah.
So I'm just saying maybe it's just practice.
Yeah, there's. I see. So in the example with the robot arm, the one robot arm, it you can do motion capture. The example being shown there is actually from a human motion capture trajectory, and it moves more or less like an arm might move. And the other one that was going didn't look very impressive at all. Those are both the same robot. So the robot itself has the capabilities to move. The bottleneck, and do I have this on my next slide, maybe? Do I have it? Oh no, this is that slide. Let me go back. So the capabilities, I'm jumping ahead in what I was going to say, but that's awesome because you pulled that one out early, is in fact that it's not even, in many cases, the human's capacity to provide information that is used in the direction of a device. And it's not the capability of the device. It's that somewhere in the middle, the bottleneck is in fact the technology that interprets the intent of the human and is able to project that into the movements of the device, and vice versa, how machines communicate back to people. So we're missing a fundamental technological component, which is that bottleneck. And in fact, our intelligent systems technology is starting to form a very functional, wider pipe between a person and a machine that will let them actually use all of that functionality. So right now the functionality is there, but people just can't use it, is maybe the simple way to say it. I'll show an example of cool robots because I like cool robots, not because this one's cool too, but in this particular case, just to maybe to drive home that point, if you haven't seen this, who's seen this video already? Okay, you've seen it? Okay. No one else has seen this video? Okay. This is an older video actually of the Atlas robot by Boston Dynamics. There's a newer video where it does parkour and things like that and dive rolls. But I mean, we're starting to see this is an unwired system that our robotic systems they're no longer the things that go that we're seeing robots. I should update this, make a next slide as well. There's one where the robot is literally doing dive rolls. It does a handstand and then into a gymnastics roll. It does parkour up a series of objects and is running. You can see the hips flexing as it moves in really well balanced motor behavior. It also does this, which I think. So I mean, don't lose hope. Robots aren't perfect yet, and I think it's this one I like. Yeah. Okay, so but all jokes aside, if this was even 15 years ago, that would have been millions of dollars of repairs. And right now, these things can just stand up by themselves and keep going. Maybe not the Atlas robot, but the Spot Mini and things. They can just get knocked over, fall down, pick themselves up, and not have $1 million worth of damage. So I showed you that in part because to keep going on the point that you brought up, is that, I mean, we're starting to see, this is one technology I didn't show you, which is exoskeletons, but we're starting to see that people are now wearing robots as well. People who have limited mobility or impaired mobility, and even people who are healthy but wish to be able to not injure themselves during the line of their daily work, like factory workers, are starting to engage with robots on a day-to-day basis. And as you can see, you saw the robot doing backflips in the other slide. That robot could very arguably be attached to someone's body. The person could be riding inside a robot like that. But there's something missing. There is still a piece missing that sort of gets in the way of the person actually using that system to do backflips and all those other things. And, oh yes, please, go ahead.
So I just actually had a question. So you're talking about, I found it really interesting how you're talking about the bottleneck and interpreting that intention into what we actually want to manifest. And admittedly, there are times where I think things that I know I will never do, such as I'm at the grocery store, I'm in the wait line, and I think, man, I could really punch this cashier right now, but I won't.
I'm glad you didn't.
Yeah, but there are these just thoughts in our heads that we never want to manifest, but happen subconsciously, and they're just there. How would we even want to approach this when we're considering how we want to, when we're considering this bottleneck, where we can decipher what actions are appropriate and what actions aren't? Because, even though we'll think, oh, I'm not going to do it, that thought is still there. And what if, a prosthetic will go reach out and punch the cashier?
Yeah.
So I'm just wondering, like, how will we ever go on about approaching that?
Right, so I mean, this is a great point because let's imagine I'm assistive technology floating on your brain.
Yeah.
And if I can't tell the difference between your actual monologue and your internal monologue, like if
Yeah.
I can't tell the difference between your hypotheses or your posits or your rollouts and your simulations and the actual motor intent that you wish to perform, then you're right, we have a big problem.
Yeah.
Because it's like the genie that listens to everything you say and makes it all become a reality. That's a really scary possible outcome. The separation that I think requires, so again, I like to break things down into data, decisions, and goals. One is that you could imagine that the system that is incorrectly punching out the cashier on your behalf did not have correct data or window into your mind to actually make a good decision. So that's one possibility. Like it's very possible that, in fact, it didn't have a good enough window. So if we sample in certain ways that are impoverished, perhaps it's just sampling only the rudimentary information and not also sampling the part of your brain that's saying, actually, let's not do that. Right? So one, it could be the data. It could be that there's a misalignment of goals. So it could be that it's not well capturing your goals. Maybe it doesn't model your goals well. Like, are you a person who wants to cause harm on other people? Maybe it's not modeling its goals or aligning its goals with your goals in an appropriate way. Maybe the way it makes decisions is flawed. So maybe it hasn't had the opportunity to be trained by you as to what to interpret and what not to interpret. Maybe its decision-making mechanics are very black and white. So we can start, I think we can start to break down, especially in terms of what does it predict the outcomes are going to be of this action? How does it represent the situation? Does it represent the situation with a bit that says, yeah, punch everything out, I'm in the boxing ring? Or I'm in a social setting where typically physical contact with other humans is avoided. So imagine it represented the world it parsed the world in some way. I'm just in a hypothetical situation, parsed the world in some way, and it had a bit which was on, which is I'm in public, and I'm not undergoing a threat, and therefore I probably shouldn't, then you can imagine the next thing would be, in these situations I predict that the person that I'm working with never physically interacts with other people in the situation, therefore I will not fire an action which moves the motors of my fist towards someone else, even though there's that coming out of the brain. The extra context and the extra predictive structure around that might be safeguards, if done correctly, on misinterpreting a cue or a situation. So I think that impoverishment in any of those ways starts to zero in on the problem case.
Okay, yeah. So, but I was also thinking, what if you were in a context where you might want to punch someone, but you wanted to show restraint and you just couldn't, the machine kind of just takes over for you because even though subconsciously you wanted to punch someone, you actually wanted to hold back. So there's also various ways you can also approach this thing, and I feel like it takes it might take a long while before the whole system's perfect.
Yeah. People do this too. So I love that there's more questions and more comments. So we're going to move on to those questions and comments. But I like this especially because people do this. People punch people out all the time when they really, really don't want to. And our own motor systems are not arguably not single point decision making systems. We have many coupled systems as well. And I think this is just another coupled system that has to fit into that because people make bad decisions all the time, even though they really don't want to. And they still do it. Or they go out and they have a few drinks that they shouldn't have had. And then they make even doubly bad decisions, and they're making all sorts of crazy decisions that they know they don't want to do, but they're still doing them. I don't think that our neuroprosthetics are arguably any more than an extension of that usual decision-making process if they've been given the right window into the mind. In which case, people still have to control their minds. We can't cop out. And if we cop out, then maybe we're building systems that govern or regulate our own minds. And maybe that's a concern as well. So maybe we just have to be really good about controlling our own minds and not thinking what we don't want to act unless we're explicitly simulating in a certain way. Okay. Sorry, comment, yes.
Yeah, but what if you actually did want to punch someone and all the safeguards made it so you couldn't? What if it's a self-defense situation? So there's also that possibility where you want to punch someone so you can't.
So, but this is exactly the counter as well. If the system is very well governing you and says, well, we never punch people, that's bad for society, so I'm not going to let you punch someone, and you're actually in a self-defense situation, that is actually a problem as well, right? So that's the counter problem, and it is also hard. clearly at that point, in both these cases, it's setting up a larger window between self and other. One view you might have is that when you're working with assistive technologies, that the assistive technology is one person and you're another person. You work together as a team. The other perspective, and I'm not saying one of these is good or bad, is that you and the assistive technology, you and the intelligent system you're working with are in fact the same thing. Much like our brain is a composition of many different little decision-making units, you might imagine that you plus a neuroprosthetic is also just you, but it has more computational processes that are bolted on. And so then the question is, are those well aligned? Are those computational pieces well aligned or not? And you just both showed two different examples of how you might have massive misalignment or situation misalignment. And so how we address those, again, I think goes back to coming up with clear definitions of how the machines are interpreting, acting, making decisions, simulating, synthesizing, representing, and then trying to address the problem from those vantage points, from those traction holds, as opposed to then trying to address it head on without having to hold. One more, yeah, you had a comment? Oh yeah, then, yes, please. Oh wow, that's okay.
Yeah, I mean, just very quickly, I sometimes worry that we tend to oversimplify the whole comparison between, what's intelligent and what's simulation. Your examples are good ones. So say the minute or two that you're in a line at Safeway, and you imagine, you could clear your brain and not let it be, but I don't think that's how most humans work.
Mm-hmm.
And if you really think about it, while you're standing in that line for a minute, you have dozens or hundreds of thoughts that are going through your head, are quickly evaluated and dismissed, and would include the possibility of punching not only that person but anybody around you. As well as when an altercation, something unexpected breaks out. People behind you, somebody's picking on someone else and they start pushing each other. You're bearing witness to this. When you think about how many thoughts go through your head as to whether you should intervene or not, many thoughts per second for sure, which in that sort of situation result in a decision. Either you're going to jump in or you're going to jump away. And when you think about it, you realize, I thought, I looked at each of those people, I did this quick assessment of what their intention was. So sometimes I just worry that when we're talking about intelligence, we can only scrape the surface of what the brain is doing. Is it essential for the brain to go through all 100 possibilities before we actually decide to act? I'm not sure. I just know it's very complex.
Are we out of time? No, we're out of time. Okay.
Somebody wants Dr. Souls.
That's, I think that's really, I like this as well because I do think that we underplay the complexity and we study systems in less complex settings than we might well study them in to actually start to get towards that, because the level of complexity that our brain handles is, as you point out, very high. Do we expect a system to be able to operate in a similar level of complexity and parallel with us? Maybe people do, but maybe we shouldn't. Now, can we bolt modules onto human decision making that leverage all of the innate human processing and then amplify the aspects that we find most beneficial? Maybe that's the camp I'm in. I'm thinking, in fact, yes, there are ways that we can amplify our own potential to maybe more quickly make that decision of whether or not to intervene. What is the right action as we do it? Maybe we can amplify those cognitive powers. So it's not so much even that the system is trying to override or to execute upon, but maybe it's just trying to make bigger the thing that we already do or make more fruitful the thing that we already do. The other piece that I thought was interesting, and it came up while you were saying that, is that, we often expect that we don't adapt to technology. That goes back to our discussion earlier. But it's actually fairly reasonable to expect that people who are intimately connected to other kinds of non-biological decision-making systems, like someone using a robotic limb or someone with a decision support system, a doctor with a decision support system, that they may actually have to change the way they think too, or that it's inevitable that they will change the way their own brain operates. Our brains are highly plastic systems. I think we should expect that maybe people who use neuroprosthetics will in fact develop different thought patterns, different ways of thinking, different ways of controlling their own mind. We know this is true for people using brain-computer interfaces right now. Someone using a BCI and they're trying to drive a wheelchair with their BCI. They can't move their body below their neck. They're trying to drive it through a small opening. They have to focus their brain, they have to clear their brain of other thoughts because the EEG cap is relying on them giving very clear signals so that they can move their assistive technologies. So people are in fact fine-tuning the way that they think. Our prosthetic users are learning how to very precisely control small muscle groups using their peripheral nervous system so they can give clear signals to the machines that are helping them in daily life. And so I think it's not, like, we can't put all of the load on the machines to interpret our muddy, murky, muddled, crazy human minds, is that we have to tame our own bodies and our own minds to better, more clearly communicate with our partners, if those partners are machines, or if they're humans. When we're interacting with other humans, we also have to be very clear. So I think that's a side point as well, that we should expect humans have to change the way that they interact with intelligent technologies, simply because it will allow more clear communication channels. Sorry, I know you had your hand up, so I was gonna, oh wow.
And just, so do you think the bottleneck is occurring simply because of anatomy and physiology? Like you're pairing a machine made of non-organic chemicals, like not carbon, hydrogen, oxygen, like nitrogen, and so on, and to mimic like the finesse and the refinement that neurons give, like the thousands and millions of connections and thresholds and all that, wouldn't that be just the major and most obvious reason you're getting a bottleneck? Or I'm just coming from a cell biology perspective.
No, you're bang on. In a minute, I'm going to skip that slide because it's probably important. I'll go back to this slide. There's a diversity of signals that flow to and from the human body. And let's just imagine the case of an assistive machine, any of the ones we talked about. There's a diversity of signals that flow to and from that machine as well. The number of those signals is highly varied. So it might be that we maybe we can only record 2 or 3 things from a person. Right away, we're going to get a bottleneck just because of the sheer channel carrying capacity of those remaining modalities. The other is that they vary in terms of how information is conveyed in terms of both space and time. So if you're looking at say neurons, they're going to be firing action. There's going to be action potentials. There's going to be like little spike trains that are going down. Those are separated in time. There's a coding in time. Really smart folks in Europe have done some awesome work, like Dario Farina has done some cool work in decoding the spike trains based on the biology of the arm, let's say, so that to actually be able to fill in missing information because of the way that temporally extended sequences of signals interact with physical tissue. So there's like this, we're losing information all the time because let's say our natural system is designed to both send information efficiently in both time and space, like which nerve do you put it on, which axon do you put it on, and then how do you time sequence on that axon, but also because our body is a physical decoder for the information. So we're losing a lot of stuff. Also, I think we're losing, there's also aspects of how we perceive the world that in some ways are shipped down to the pieces that have to make other decisions. When we connect an assistive machine, we're asking it to also know things about the rest of the world. And that is also a missing piece. So there's also a loop here where the world communicates information between a person and a device. So I think there's a lot of reasons for the bottleneck. In assistive rehabilitation technologies, a fundamental part of that bottleneck is the fact that when you have a problem, like someone loses part of their limb, you're trying to replace that part of the limb, and the more you lose, the more you need to replace, but the less you have to figure out what information was supposed to go to the thing that was replaced. So you keep losing every time you start, the higher you go up with an amputation, for instance, the more motor control. If it's just a fingertip, well, you're just replacing this. If it's a wrist, you're replacing all of this. If it's a shoulder, well, you're replacing all of these motor commands, which the range of possible motions for my arm is astronomical. And you lost all those other signals that you might have used to actually infer what the person wanted. So part of the bottleneck is, in fact, in rehabilitation, is just that you decrease the number of available signals you could use to infer human intent. But you're right, there's a lot of other factors. It's modality, it's materials, it's that brains hate having hard things stuck in them and wiggled around. Yeah. Yes, and then, yeah.
I was just gonna ask, so when you're connecting this interface to the brain, where does it actually go to? Is it the primary motor cortex then?
It depends on what people are doing.
Like if it's the arm that you showed us in the video.
Yeah, so they have a little bit in the motor areas and a little bit somatosensory areas, was what they were doing in there.
Okay, yeah.
There's two plugs, one here and one here, so in that case, that's where they were connecting. People have put wires in a bunch of places, and it really depends on exactly, typically, traditionally, we are very bad at recording lots of things from the brain in parallel. Elon Musk has done some crazy stuff with Neuralink recently, where the density of recording and the ease of creating those recording apparatus has gone up dramatically. So like Neuralink has this little sewing machine that can start to sew like flexible electrodes into the brain. And yeah, that looks really promising for getting more channels, but typically people have to pick, because we have these little tiny Utah arrays with like 100 things, where do we put this? And so people have typically put it in places where they think they can record easily the kind of motion they want. And so your example is exactly like, yeah, let's just pop it in the motor cortex, somewhere around the body part that we think is the one we want.
Yeah.
And then we'll like look at all those signals, and some of them are garbage, and we'll use machine learning to filter out the garbage signals. And for the remaining signals, we'll use another kind of machine learning to map them to motor commands, because clearly the motor commands must be there. Downstream in the peripheral nervous system, more or less the same thing. You're like, well, let's put electrodes on the muscles that we know relate to the different movements we want, or the nerves we know, and then we'll filter out the garbage ones and try and pull out patterns from the ones that remain.
Because even then, like all this self-control, that doesn't belong in the primary motor cortex. Like that's more the frontal lobe, and that's not affected if it's a spinal cord injury. So that'll get projected to the motor cortex.
Yeah.
So like that self-control still exists. Like I would assume in
Yeah.
moving arm if it's just in the primary motor cortex. But then another thing that seems to be missing is like the proprioception,
Yep.
like just having that
Yeah.
feedback back to the brain just to know where the arm actually is. Has that, like there's no sending back to the brain yet, it's just
No, there's a ton of work on sending back. We've done a ton here at the U of A actually.
oh,
So like kinesthesia and perception, my collaborators, Dr. Jacqueline Hebert and others, have done a ton of work on rewiring the nervous system to be able to send back signals, looking at simulating kinesthesia and proprioception, using different modalities on a residual limb of someone with an amputation. People have looked at direct brain stimulation and peripheral nerve stimulation. There's an entire effort down in the States over the last 5 years that was really trying to like
Yeah.
close that loop in a pretty substantial way. Either direct to the brain, peripheral nervous system, or to tissue attached to the peripheral nervous system.
Because even that itself would
Yeah.
speed up the learning process because the feedback is back and forth.
You
So-
need the feedback.
Yeah.
You're bang on. Like without the
Yeah.
feedback, it's a really hard learning problem for the
Yeah.
person. So that is also a huge. That is a huge piece of it. Is that we do expect you'll need to do that. The piece about your comment about the motor cortex maybe having all of the inhibition as well. The tricky piece, and this I don't know how people have decoupled this, is that if I watch you throw a baseball, or imagine you throwing a baseball,
Oh, yeah.
that same area of my motor cortex lights up as if I was doing it myself.
They're mirror neurons, I remember.
Well, yeah, people don't know whether mirror neurons, they're like, do they really exist? What about those mirror neuron things? And some people are like, yeah, they totally exist. And some are like, they don't really exist, or we define them wrong. Anyway, regardless of what you think about mirror neurons, people have called that kind of phenomena, yeah, the mirror neuron.
Yeah.
And it's tricky, because then you're like, oh wow, I watched you punch the cashier in the face, and now you're punching your own cashier in the face. Yeah, this is maybe the worst example we can use for making people not scared of technology. Yeah, cool.
And just like one more thing that came to mind when you were talking about like how far up the limb is amputated, as well as with like the plasticity of the brain, does it depend how far after the injury the prosthetic is inserted? Because the motor cortex, it's like changing, especially if it's an arm, that area for the arm will change. Maybe it'll be used more for the, I don't know, like for the face now instead of the arm, stuff like that. So if that motor cortex does change, can you still control the arm even though it's supposed to be the face?
Our experience is that people can,
Yeah.
in the long-term downstream. I'm not the right person for that. My colleague Paul Marasco or someone else have done actually extensive studies on that kind of thing. One thing is that, I mean, if you blindfold yourself, the part of your cortex that would have been using that information doesn't stay dark either. In fact, other parts are already using it. So there's in Norman Deutsch's book, Brain Changes Itself, I think there's some good examples of this as well. But that like the minute you occlude it, these patterns will fire up. The minute your eyes come back, they take back over that part of the real estate. So turns out maybe we don't lose our patterns too easily. Okay, thanks. I didn't get to your question. I'm sorry, but I know you got.
You actually answered it. It was part of the question she asked, so that's okay.
Oh, okay, cool.
I just have class.
I do think we are at 3:19, so maybe, I didn't actually have anything left except this, which is that, hey, I just showed you a device, but really it's everything else in the world. Like, these technologies are allowing us to connect ourselves to the wealth of sensory motor information in the world around us, something, and that's not just true for patients, it's true for you, it's true for policy makers, it's true for caregivers. Really, we're looking at ways to extend our decision-making processes out to the world around us. Machine intelligence is the glue. That's the end of my talk. Hooray! Thanks, everyone. Thank you for the great questions. That was one of the best discussion sections we've had in quite a while in giving these lectures, so I really appreciate it. Cool. Thank you, folks.